Leetcode 227, Basic Calculator 2. We are given a non-empty string s, which represents a valid mathematical expression. We need to evaluate this expression and return its value. This string is made of non-negative integers, of 0, 1 or more operators, plus, minus, multiplication or division. It can contain white spaces, and the division should truncate towards 0. The challenge here is that we have two sets of operators with different precedence or priority, and we need to use operators with the greatest of precedence first. When we have two operators with the same precedence level, then we evaluate from left to right. So for example, given 1 plus 2 times 3, we need to evaluate 2 times 3 first, then evaluate 1 plus 6. There are at least 4 ways to solve this problem: using 2 stacks, using 1 stack, using only a few variables, or using a grammar. The first solution is unnecessarily complex, so I'm going to skip it. The one using 1 stack is reasonable. It's not obvious, but I think one should be able to figure it out. Then if we push the reasoning a bit further, we can get rid of the stack. So I'm going to show you these 2 solutions, and then I will show you how to solve this problem using a grammar, because I think grammars are powerful and useful tools that you can use to solve this type of problems in real life. For the 3 solution I'm going to show you, we are going to read the input string character by character from left to right. For the first solution that uses a stack, the main idea is that given an expression like this one, we are going to convert it into a sum of terms. In this example, we have the terms a is equal to 1, b to 2 times 3, c to minus 4 divided by 2 times 3, and d to minus 7. Each one of these terms will be pushed onto the stack, and then we will just pop everything from it and add them together. Now the question is, how do we construct these terms? This question leads us to another question, which is, which term is the current number we are looking at part of? The first number is obviously part of the first term, but what about the second number? We have a plus before it, so here we are starting a new term. So the number 2 is part of the second term. Now what about 3? Well, it has a multiplication in front of it, so it's part of the second term, which is now composed of 2 times 3. Then the fourth number in the expression is preceded by a minus, so we need to create a new term, which contains the value minus 4, and so on. Here, what's important to notice is that the term to which a number belongs to is determined by the operator before it. If it's a plus or a minus, then we need to create a new term. Otherwise, if it's a multiplication or division, then it's part of the current term. To make our life easier, we can imagine that there's a plus in front of the first number in the expression. So now let's write some code. We create a stack and a variable to hold the operator before each number. We initialize it to a plus to help us create the first term. Then we loop through the characters in the expression. If we see a space, we discard it and go next. But if we see a digit, it means that we are starting to read a number. So what I like to do is keep the starting position of the number, then increase the value of I until we find a character that isn't a number, or until we reach the end of the string. Once we're out of this loop, we can extract the string and cast it to a number. Now, the downside of this method is that we must not forget to decrement I, because if we don't, the for loop is going to increment it, and we are going to skip some characters in the expression. Okay, now that we have a number, we need to decide what to do with it. Should we create a new term or modify the last one? Because it depends on the operator before it, we can use a switch on the operator. If it's a plus, then we create a new term by pushing the number on the stack. If it's a minus, then we create a new term containing minus num. But if it's a multiplication, then we take the value of the last existing term by popping the stack and push onto the stack this value multiplied by the number we've just read. And it's the same idea for the division. We pop the value of the term we are constructing, we divide it by num, then to respect the requirements, we truncate the result and push it on the stack. Okay, so we've seen white spaces and numbers. We just need to deal with operators. So when we see an operator, we store it inside the variable op. And that's enough to construct all the terms. Once we're done reading all the characters, we will have our terms inside the stack. So we just need to add them together to get the final result. And that's it. Now, if we pay careful attention to what the stack is doing, we can realize that we don't actually need to use a stack. First, whenever we construct a term, we only store one number at a time. For example, if we have the expression 3 times 4 times 5, then we will push 3, then we pop 3. We then push 3 times 4, which is 12, then we pop 12 and push 12 times 5, which is 16. So we could do all of this work in one variable. In our current solution, we also use the stack to store all the terms, and at the end, we add them all together. But we don't actually need to wait until the end to add them together. You know, as soon as we have a new term, we can add it to the previous one. For example, consider the expression 1 plus 2 times 3 minus 4. We push 1, then push 2, then we pop 2 and push 2 times 3, which is 6. Then, because we are done constructing the current term, we can pop 6 and 1 and push 1 plus 6, which is 7. If we keep going, we push minus 4, and because we reached the end, we pop minus 4 and 7, and push back minus 4 plus 7, which gives us the final result. So as you can see here, the stack contains at most 2 elements. The first element is the sum of all the terms we've seen, while the second is the current term we are constructing. So instead of using a stack, we only need 2 variables. Let's call them sum and term. Now it's pretty much the same idea as before. So picture this. At any time, we will have the sum of all the terms we've already consumed, to which we want to add the term currently being constructed by looking at the rest of the expression. Now, if you recall what we said earlier, to know if a number is part of the current term or a new one, we need to look at the operator before it. If it's a multiplication or a division, then it's part of the current term, so we multiply it or divide it by that number. But if it's an addition or subtraction, then it's part of a new term. So what we need to do is add the current value of term to the sum of all terms, and then we assign num or minus num to term. Okay, we just need to be careful at the edges. At the beginning, because we haven't consumed any term, we can initialize sum and term to 0. And because the expression starts with a number, we can pretend that there's a plus in front of it. So we will initialize up to plus. At the end, the variable term will contain the last term. So the final result will be sum plus term. Okay, I think we're ready to write some code. If we start from what we wrote previously, we can delete the stack and every reference to it. Then we can create and initialize our 2 variables, sum and term. The variable up already contains a plus. So now, after seeing a number, if the operator before it is a plus, then it means that we are starting a new term. So we add the value of term to the sum, and we assign num to term. If the operator is a minus, then same thing, except that term is assigned the value minus num. But if it's a multiplication, then we just multiply the term by num. And if it's a division, we divide term by num, truncate the result, and store it inside term. And finally, we can return the sum plus the last term of the expression. And voila. Okay, these 2 solutions work well, but they are specific to this problem. So I would like to present a more general technique that can help you solve a wide range of similar problems. We are given a valid expression. Valid means that it is made of specific symbols, so numbers, operators, and white spaces. These symbols together form a set called an alphabet. Here, spaces are irrelevant. Ignoring them doesn't change the meaning of the expression, so we're going to pretend that they don't exist. Valid also means that expressions follow some syntactic rules that describe how to use the symbols of the alphabet to make valid expressions. For example, if we want to describe the set of all possible additions of two natural numbers, like 1 plus 1 or 2 plus 3, we can use the following rules. An expression is a number plus another number, and a number is 0 or 1 or 2 or 3 or 4 up to infinity. Of course, we are not going to list all numbers. Instead, we can list the first 10 digits, surround them with parentheses, and add a plus sign like this to indicate that there's one or more digits. These rules are made of terminals and non-terminals. Non-terminals are variables that can be replaced or expanded by their corresponding roles. Here we have the non-terminals expression and number. Terminals are symbols of the alphabet and cannot be expanded. Here, the digits and the plus operator are terminals. These rules are called production rules because starting from the start symbol, which is the non-terminal expression, we can produce any valid string. For example, an expression can be expanded into number plus number. Then we can expand a first number by replacing it by 1. Then we can replace the second number by 2. This process of building a string of terminals from the start symbol is called a derivation. And each of the strings generated by a derivation step is called a sentential form. Together, terminals, non-terminals, production rules, and the start symbol are called a grammar. So let's write a grammar to solve our problem. We already know the terminals we can use. The start symbol will be expression. We now want to create non-terminals and production rules that describe all possible valid expressions. We could define an expression as being a number followed by 0, 1 or more, plus, minus, star or slash, and a number, but this wouldn't be very useful. A more useful grammar is one that expresses the order of precedence of the operators. To do that, we want to have one production rule per level of precedence. We usually write production rules from lowest to highest precedence. So we can write that an expression is a term, or the sum or subtraction of multiple terms. And a term is a number, or the multiplication or division of multiple numbers. The reason why this grammar is good is because any valid expression can be expressed by a unique derivation tree. Every leaf of this tree is a terminal and all the nodes are non-terminals. And evaluating an expression is equivalent to doing a post-order tree traversal. To do that, we can make a function for every non-terminal. The body of these functions will correspond to their production rule. To make our life easier, I separated the code into two components. A scanner that will take the input string and scan one token at a time, and a parser that will evaluate the expression. Let's take a look at our scanner. It's an object that stores the expression string and its current position in the string. It has two methods, scan token and pick. Scan token is used to scan one token at a time. It first starts by skipping all white spaces, then check if it's the end of the expression, in which case it returns some arbitrary token that I called end of line. It doesn't really matter. If it's not the end, and if it sees a number, then it constructs and returns that number. Otherwise, it's an operator and returns it. The scanner also has a pick function that returns the first character of the next token that will be consumed by scan token. You will see this is going to be useful for the parser. Okay, now for the parser, I created this parse function that takes a scanner as a parameter. Inside it, I create one function for each non-terminal. We can implement them by looking at the production rules. So an expression starts with a term, then it can be followed by a plus or a minus and another term, 0, once or several times. So while we see a plus or a minus, then we store the operator, scan the next term, and apply the operation. Once we're done, we can return the results. For a term, it's the same idea. A term is made of a number, optionally followed by one or multiple multiplications or divisions. So while we see a star or a slash, we store the operator, scan the next number, and perform the operation. At the end, we can return the results. For numbers, it's even simpler because they are simple tokens returned by the scanner. Now that we are done defining the non-terminal functions inside this parse function, we just need to call the expression function to return the value of the expression. Finally, to solve the Leetcode problem, we just need to create a new scanner and call the parse function. That sure took us some work, but believe it or not, you can create simple programming languages this way. I skipped a lot of important details to make sure this video isn't too long, but I'll talk more about grammars, parser, and theory of computation in future videos. So subscribe for more, and if you would like to help me make more videos, consider becoming a member.